Good morning everybody. In this last class of D and F block elements, we will just today discuss about the features, the electronic configurations, the oxidation states of the F block elements. And basically what we will be seeing here is how we can locate the F block elements, and there will be two different F block elements. One is 4F and another is 5F. So, 14 plus 14, because we know that the maximum capacity of F orbitals is 14 electrons. So, there are 7 orbitals, each of them are occupying 2 electrons. So, 7 into 2, that means 14 electrons will be feeding in the periodic table for 5F as well as 4F. So, basically what is our intention, that how we can identify these elements, because we do not have any scope to study the reactivity pattern, the reactions and all these, but there are some examples which are very well found in the nature. So, basically when we get all these elements from the minerals and the ore, so these can also be related to some amount of the corresponding geochemistry, which is a very important subject and a huge subject, where people can handle the different ores and all. And this geochemistry study for these periodic tables, because if we locate these elements in the periodic table and how we can place them depending upon their properties. So, initially we will see that how we can locate or find out these 4F elements, and those 4F elements whether they are interesting for their oxidation state and the reactivity or in some other type of applications. So, geochemistry is basically dealing with the nature, because the nature is the typical source for getting all these elements, and in the nature occasionally we say some of them are not very common on the earth crust, like iron, like zinc, like nickel, etc. So, they are basically called as rare earth elements or the rare earth, but they, when they found, they are combined together, they are found together in the nature, and that is why they are all called as the rare earth elements. So, if we just see these two groups, so we have seen the different properties of 3D, 4D and 5D elements, and side by side what we will be getting those 4F and 5F elements. One is the corresponding lanthanoids starting from lanthanum, and other is the actinoids after actinium. So, as we are dealing with 3D and the 4D on the 5D, we have seen that the other orbitals which are involved along with they are very nearby, energetically they are also very close. So, in case of this 5F and 4F, we will see that several D and S orbitals will also be there. So, we should also consider particularly the occupancy of these D and S orbitals along with 4F and these D and S orbitals along with 5F, because for getting the different oxidation states, these are initially from the elemental state, that means the lanthanum, the series starting from the 0 oxidation state, that means the metallic or the elemental form, it can go to lanthanum 3 plus with the loss of 3 electrons. So, those 3 electrons can be lost from S and D levels. So, let us see how these groups can be considered. So, since they are inside the transition elements, that are called as inner transition elements, because when we reach the transition elements such as that of our 5D or the 4D, they are filling beforehand. So, these inner transition elements, so transition elements, they are of inner type, they are having 2 series, as just now I told you, they are lanthanoids and actinoids having 14 elements in each series. But what about their electronic configurations? The electronic configurations are always important, because the reactivity patterns what we have just discussed in our previous classes, that the D block elements. So, D block elements are there where we see that the 10 electrons can be introduced in the different d levels or the d orbital, starting from a situation which is also very much useful and characteristic is the d0 state. But in the elemental state it is not d0, but also in the ionic state it can be a d0 situation like that of our manganese 7 plus 7. So, this electronic configuration can be very useful to know, and what are the different oxidation state, particularly the most stable oxidation state is important to know. So, mostly they are all tripositive pions. So, tripositive pion which was not common for the transition elements, the d block elements, because in case of d block element mostly we find that the +2 and the +3 oxidation states are very much prevalent. But in this particular case it is the tripositive ions which are very much stable. So, if we can knock out the s electron, 2 of the s electrons and 1 d electron without touching the f level, we get a situation where the element will be in the tripositive state, and we can have a particular configuration for the 4Fm level. Since for the d level we are using n is the number, similarly for these inner transition elements or f block elements we will be using m for the number of electrons occupying this particular ionic state or the elemental state. So, we can have f, that means 4F0 to up to 4F14, and like that of our d block elements it can have some extra stability corresponding to those oxidation states or the elemental state. Okay. So, in terms of these general features which are very important to know, because this is there in your book also very nicely collected over there, because the general features will tell us that how these can be known first and what are the positions in the periodic table and any reactivity pattern, particularly any application. So, if we know some reactivity pattern like that of our d elements or the 3D elements, we can see that they can be very useful also along with the 3D elements. So, 3D elements along with the 4F elements can be very useful for particular type of properties like that of our catalysis. Then sometime we know that which is not there in your syllabus, this is organometallic compounds. Organometallic compounds are nothing there, the name will tell you that if you have a organic part and a metallic part like that of your very well known thing which you study in organic chemistry is the Grignard reagent. So, methyl magnesium bromide or phenyl magnesium bromide. So, you have the methyl or the phenyl which is attached to the magnesium. So, the carbon attached to the metal, that means the metal carbon bond if you have. So, organometallic properties or the organometallic compounds we can get from there also. So, what are the general features for in the elemental state, what we get from the different ores, and we will also see very useful and well known ores like monazite. We will see what is this monazite, like that of our pyrolusite and hematite, magnetite like of ores. So, these all lanthanides are silvery white soft metal and which are tarnished if we keep in air, because some oxide layer is forming, some oxidation can take place over there. If they are reacting slowly with air, sometimes it can also react with carbon dioxide and moisture. And as we move from left to right, the elemental condition or the elements, their hardness basically increasing as we move from left to right. And when we reach to samarium, is not that at the end of the series we reach samarium, and samarium is still hard metal. So, melting points is also will be increasing. For samarium case it will be 1623 K Kelvin. So, which is way above to that of our 1000 and 1200 degree K for the other species or the other metals. So, this can be compared to their metallic state, what we get that this melting point and hardness and all these, because sometimes we have to use these as material, because the material characteristics apart from the catalytic and all other behavior which is also important. So, material wise if we want to use that for some to increase the hardness or to increase some other property, we can use these species. So, this particular one from following this lanthanum. So, this lanthanide series. So, from lanthanum to lutetium we get all these elements. So, basic feature is that there is no need to remember all the name of these, because it is sometimes very difficult to remember all these things. So, you should not try to remember all these metals, but at least you should know that some of them are very useful and what is their electronic configuration and what is their position, particularly the atomic number. And if your atomic number is given to you like that of a cerium, because cerium we all know is a very common metal salt what we use in the laboratory, which is a ceric ammonium sulfate or ammonium ceric sulfate. So, which can also be like your Morse salt, which is a double salt. So, which is a very useful oxidizing agent also, because later on we will see that along with potassium permanganate and potassium dichromate, we can use this particular ceric sulfate. The sulfate form is very useful, because if you use sulfuric acid for the redox titration, can also be a very useful oxidizing agent using a particular species or the metal salt which belongs to a 4F category, or which is a lanthanoid. So, this one where in the species is all the elements elemental form of cerium. We are having electrons in S level, we are having electron in the D level, and we are having electron in the F level. So, this has a particular electronic configuration that we also remember, that 1, 1, 2 electrons are there in all 3 levels, and they are very close to each other in terms of their energy differences. Similarly, if we move to gadolinium, so gadolinium when we reach to the F7 condition, so it is also instead of F1 it is F7, D1 and S2, and lutetium which is also F14, D1 and S2. So, in all these cases what we will be getting there, that if we remove all these electrons from the 5D level and the 6S level, you get a corresponding tripositive species. So, tripositive species is the cerium 3 plus. So, cerium 3 plus will have electronic configuration of 4F1. So, this electronic configuration is very useful, because still you have one electron in the F level, and in terms of its redox potential value, whether we can still take out this particular electron from the F level, we can reach up to an oxidation state of +4 for cerium. And in true sense, the cerium can go for a condition where the cerium can reach up to a oxidation state of +4. Similarly, for this particular one, the promethium, if we can remove one more electron from here, and for the terbium, if we can remove one more electron from here. So, this gives you a F0 situation, so which is not filled basically, which will have some stability like this 4F0. So, this 4F0 situation we get that there, and in this particular case also for promethium and terbium, that if we take out one more extra electron from this 4F8 situation, it will again be 4F7 like that of gadolinium in +3 oxidation state. So, they have some extra stability for the half filled cell, as we all know for D5 situation in the transition elements. Similarly, for this particular one for the terbium as well, we get this particular oxidation state as 4F7. So, these are the positions. Without memorizing the positions of all the entire series, we can have some idea about the positioning of the cerium and why we will be getting some half filled situation like this, because in this particular situation when we get the bivalent state, we still have a d electron in it. So, instead of F8 situation, we have a D1 situation. So, D1 F7 situation for gadolinium in bivalent state. So, one condition is that how good they are for the corresponding highest possible oxidation state. So, in case of these highest possible oxidation states, we have written down only 5 of those elements. So, cerium, promethium and neodymium and terbium and dysprosium. So, these can have some extra stability as we move for a F0 situation or a F7 situation, and along with this F7 we can have also F8. So, this basically gives us some idea about the corresponding the size. So, radius or the ionic size as well as the atomic size. So, if we just consider that they are ionic sizes, so atomic sizes also are important. Why they are important? We should ask yourself that since we have 4F level instead of the corresponding D levels, so we have 4F levels, and we all know that these are having some orbitals involved F, and they are, if they are more diffused in space, whether we can have some bigger size compared to the transition element. So, when we consider the atomic sizes, we should consider the size differences between the transition element and the inert transition element, and we should also consider the situation where we all know that is another process which is very useful for the 3D element is the alloying. That brass we get, the bronze we get due to the alloying formation, and during that particular alloying formation the size plays some important role there, and if the sizes are matching, particularly from the idea what we get for the size effect in solid state structure. So, if we can have these solid state structures, so size basically, if the size is bigger, so atomic sizes, as we see that along the series how it is changing starting from the initial point, whether it is bigger or smaller than that of our 3D or the 5D element we get for the transition element. So, the solid state structure, how it can affect as we move for the atomic sizes, as well as if we move for the corresponding ionic species, that means lanthanum in the trivalent or the bivalent state. So, these when we get these ionic species, so the ionic condition, that means the ionic sizes also like that of our atomic sizes, we can also think of about those ionic sizes and how they are different, how much they are different from the corresponding atomic sizes. So, these sizes are also typically related definitely to their radius, because your book will tell you about the corresponding ionic radius. So, there is some role to play for their size. So, they basically involved in their solid state structure, they can change the corresponding solid state structure if they are big enough. Then if you all know that we are considering a species like very simple species when we dissolve the corresponding ferric ion in water, say ferric chloride or ferric nitrate in water, we know that the hexaaccoferric ion is formed in the solution. That means the aqueous solution. So, in aqueous solution we all know that this is the condition, that means if once we go for any aqueous solution of any metal salt, it is aquated in terms of its corresponding metal ligand interaction, that means complex species is forming. So, in all cases we get basically the complex ions. So, how the size can also affect the corresponding stability of the complexes in solution. So, this is the lanthanum species, and we can have the stability in +2, +3 and +4 oxidation state, and also sometime this value is also changing. So, if this x is varying, we do not know the exact value like that of your iron, we can typically say the number is 6, but depending upon the different lanthanides we can have a different values of these x. So, also the corresponding charge which can m plus if we write depending upon the Fm configuration for this species. But one thing we can consider over here is that as the size is changing and the corresponding decrease in size, if there is any decrease in size, that we will see effectively because of that particular thing, that means it is decreases. So, ionic size basically decreases along the series. So, as the electrons are feeding into the different orbitals, we are having some nuclear charge increase, but that is not contributing to the corresponding atomic or ionic radius of that particular element or the ionic condition of that particular element. So, as the size is decreasing from left to right, so the interaction between this lanthanum lone pair and the lanthanum orbitals to that of the lone pairs on the water molecules will be strong enough. So, which will be responsible for their increase in the stability of the complexes. So, there is a increase in the stability of the complexes, that means the aqua ions which are forming in the solution. So, this is one case, and the third case what we can consider along with the effect for the different sizes is that if we find some organometallic compound, that means if we have some lanthanum which is bound to some carbon center, and if we compare that we can have a transition metal ion. So, instead of that first thing that we can have a transition metal ion and the carbon bond. In this particular case, for the lanthanum series, we can have the compound which are more ionic than the D block elements, So, if this particular bond, that means the metal carbon bond, is important for any other property, particularly the catalysis, so that will also affect the corresponding catalytic behavior of the corresponding metal carbon bond. So, we can substitute these corresponding catalyst which are having a transition metal and carbon bond to that of our corresponding lanthanoid and the carbon bond. So, what we see here therefore, that as we see that from left to right the size is decreasing. So, you see that from lanthanum which is 187 picometer to ytterbium or lutetium, basically we go up to that particular point where the size is basically decreasing up to 173 picometer. Similarly, for the sizes of the two other species, that means for the lanthanum 3 plus. So, lanthanum 3 plus which is 106 picometer, and towards the end if we get it is lutetium. So, if we get is lutetium which is also similar to that of ytterbium which is 86 picometer. So, this what I am saying is that is a typical data, that the size of these ions, and as we just simply compare when we have Fe3 plus or Al3 plus, and we all know that the bound water molecule over here with this lone pair, another lone pair is not involved in coordination. Similarly, for OHH, so depending upon the charge and the size, which is also important. So, the charge is there. So, ionic charge we all know 3 plus, but the size. So, charge by size ratio always we consider for the solid state chemistry, but here also the charge and size also play some important in modulating the pK value of these bound water molecules. So, this particular one, so it is this one is aluminum. So, aluminum compared to we should have some rough idea which is a non-transition element, is a transition element which is a lanthanoid, and if we just follow up our study for actinoids, we will find that in all these cases how the size is changing and how the corresponding reactivity pattern and all these things are changing, and aluminum is very small which is 53 picometer. So, this binding is very strong, and as a result we most of the cases we get that aluminum is separating out from the medium as the aluminum hydroxide ALOH whole 3. Okay. So, ALOH whole 3 is thing, and in some other water molecule can also be attached to it. It is not that it is only tri-coordinated or bound to 3 hydroxide groups like that of our water molecule bound to Fe3 plus. So, this basically gives immediately that idea that what is the pK value, and pK value is also dependent on the size, this particular size. When size is very small and the number of ligands we discussed several times in our previous classes, that the number of ligands which are bound to this particular center, that means the metal ion, the central metal ion, and the geometry whether it is octahedral or some distorted one, that will also contribute to the corresponding pK values or the acidity. So, this is one aspect, that if we have a smaller size of the ion, definitely your pK value is less, and this particular proton is acidic and it can go out as H plus. But what about this lutetium or lanthanum in 3 plus oxidation state? And obviously, if they are forming the same aquated species, it is okay, you can apply the same rule, or you can extend the same justification for knowing the corresponding pK values. But once the size is increasing, it will have a natural tendency to bind more and more ligands, because in our next class for studying the coordination compounds, we will find that is like the sphere. So, if we have a sphere like arrangement for the corresponding metal ion, so if it is say lanthanum Ln3 plus, so it is there, and why this particular one is forming a octahedral complex of iron, because you do not have any other space available depending upon the size, because the size is the most crucial one. You can go for another bond. This is some kind of the corresponding pin cushion, and these are say these different pins. How many of these pins we can attach to that particular pin cushion? So, that will tell you the coordination number of that particular central metal ion. So, in this particular case, what we see, that since the size is very much different, you see that in this particular case the size is almost double. So, doubling of the size will definitely not allow you to go for a coordination number of 6. So, they will all have a very high coordination number. So, that is another feature for knowing the corresponding chemistry of these lanthanoids, is they are having high coordination number. So, they can go for a coordination number of up to 12. So, once sometime we ask for that, give an example of a metal complex having a very high coordination number of say coordination number of 12. So, ferric ammonium nitrate and all these cases, we will see that cerium center is there, and the corresponding nitrate is there if it is 6, and if it is in the +4 oxidation state. So, overall charge for this ferric ammonium nitrate will be 2 minus. So, how these 6 nitrate groups are surrounding this cerium. So, if we can go for a coordination number of 12, that means all the oxygens. So, all the oxygens, that means the oxygens for this nitrogen. So, this oxygen and this oxygen, and another is way out. So, this can form a chelation to the cerium center. So, 6 into 2. So, 6 into 2 of such nitrate groups giving rise to a coordination number of 12, and this all is due to the corresponding size. So, the cerium size is very big enough, and this particular thing also allow you to go for a chelation of the nitrate group, which is forming a 4-membered ring, which is not possible in case of other transition metal ions of 3D, 4D and 5D elements. So, altogether what we see, that if we have these centers and the size is changing. So, not only the corresponding size of the elemental state, that means the lanthanum from here to here, that is the corresponding sizes of the trivalent species from 106 picometer to say 86 picometer, which is also affecting the solid state structure to the corresponding coordination number, coordination behavior, and obviously that particular type of thing what we can expect, the catalysis. So, if we just simply plot, it is there in your book also. So, if we just simply plot the corresponding one, so we just typically there is a decrease in the size. So, decrease in the size in the picometer scale, what we have seen that it is in the 86 and it is 106. So, 106 to 86 is the corresponding. So, is a monotonous decrease basically. So, monotonically it is decreasing from La3 plus to Lu3 plus. And what about the connectivity, because we have also assigned that these two have some stability. So, we just now what we are discussing, that cerium and the 4 plus. So, cerium 4 plus is say around 92 picometer. So, this as the 92 picometer size will also have some effect for that particular one, which we are not getting for aluminum or iron, that it can interact with the nitrate groups, giving rise to a coordination number, very high coordination number of 12. So, which is a very useful compound. The ammonium steric nitrate is a useful compound, which is the material which can be used alongside that of our potassium permanganate and potassium dichromate. So, these are basically, we can consider these are the typical stability for the different metal ions in the tetravalent state or the bivalent state. So, they are present in a typical islands. So, as we move from europium, so europium 3 plus here. So, as we go from here to here, that means one electron change for their oxidation. So, it is the trivalent state and it is the bivalent state, and you see the corresponding one, the change in the size is so much. Similarly, for samarium it is here and this samarium is here. So, that particular change from the trivalent state to the bivalent state will also tell us that whether in terms of the coordination behavior it will give some important characteristics, or they are only stable in the solid state as oxides or some other useful compounds. So, they are basically stable when they are present in the trivalent state, and in some cases only they are stable in the bivalent state. So, this decrease, a very useful term, always we ask that what do you know about lanthanide contraction. So, this decrease is basically as we move from left to right, we are feeding electrons to the system, but we are not getting the change what we are expecting because of the poor shielding effect of the 4f electrons in the 4f orbitals. So, the size is not changing much, so can be explained by poor shielding. So, these are the things, the lanthanide contraction, how you can explain. So, lanthanide contraction can be explained only due to the poor shielding effect of the 4f electrons. So, 4f electrons are not shielding much of the nuclear charge. So, the electrons outside, they feel more attractive force from the higher nuclear charge. So, they basically contract. So, that contraction is also leading towards something where we can have some stabilization for the different oxidation states. So, mostly what we have discussed so far, that this is dominated by the +3 oxidation state, and the lanthanides or the lanthanum 3 plus compounds, the 6s electrons and 1 4f electrons are lost, and the ions have the configuration of this, that means they are following xenon. So, we are having the stable xenon configuration and some electrons in the 4f level as 4fm. So, 4fm is, if it is not there, that means if it is 4f0 like that of our cerium. So, cerium 0 will have a xenon like configuration, and that is why it is very much stable in its tetravalent oxidation state. And when we exhibit the corresponding oxidation state as +3 like that of our cerium. So, cerium is in +3 oxidation state, we are still have one electron. So, which has a electronic configuration of 4f1, m value is equal to 1. So, we can knock out this electron to cerium 4 plus. So, how good this thing is, that how easily we can remove that thing, and how good this ceric ion. So, this is ceric ion and this is cerous ion. So, cerium in +4 and cerium in +3, how good they are as oxidizing agent, that we can also check depending upon the corresponding amount of this particular electron transfer, that how quickly we can go for the reduction of that ceric ion to that of our cerous ion. So, one electron we can remove from there, but most of these cases these are the very stable species, and they are mostly stable in the +3 oxidation state. So, once we see that they are there, and is important this contraction, what we see that the lanthanide contraction is important for the transition elements which are filling off due to the corresponding electrons putting in the d levels of the 5d. So, putting these electrons after that particular contraction. So, it will also adopt some size. So, again some size is increasing due to addition of electrons to this, but this contraction is also some play important role to the properties of these 5d block elements. So, along with cerium, so cerium we can get as the cerium 4 plus, promethium we can get as the promethium 4 plus, and terbium we can get as terbium 4 plus, that we have just discussed. So, these things, so once we get, if this is the most common oxidation state like that of our thing what we get for iron, the hematite and magnetite. We know that either 2 and 3 oxidation plus 2 or plus 3 oxidation state is stable. So, naturally we also obtained that particular species as the corresponding oxidation state for the oxide, for the sulfide and all these things. But for these rare earth elements, it is one such case where Ln will be attached to some anion which is not typically found for the D block elements, which is phosphate having a charge of 3 minus. So, LnPO4, which is the common formula for the monazite. We know that India is also very rich in monazite sand. The monazite we know from in South India, the monazite sand is there. We get from monazites other rare earth elements, also sometimes the actinides, also the thorium is also available. So, this is one thing, that means the monazite ore, and another is bastnasite. So, bastnasite, there basically if we have some lanthanides, and we all know that like that of our D block elements, we are not restricting our metal as the salt of the bivalent species. So, it is not a typical carbonate, but it can also a carbonate salt along with some fluoride. So, is 2 plus 1 3. So, again it is 3 plus, this is again 3 plus. So, this is another salt. So, we get this particular one, and most of the elements when we just treat it for their isolation. So, isolation of these elements for their corresponding compounds, we basically get that as the corresponding halides, is very easy to get like your ferric chloride, and oxides. So, this can be treated for oxides. So, these are the most common for all the inner transition elements of the corresponding series for the lanthanides, and this basically give you some idea that this when we get for the species like fluoride, the fluoride is have a definitely the fluoride is a small ligand or the small anion which is attaching to the center, which is bigger or big enough. So, your coordination number will be definitely higher. So, its coordination number is 9. When it is oxide, its coordination number is also higher, but it is not 9, it is 7. So, this particular one for the formation of these, and for the cerium, basically when cerium is forming, so the ionization enthalpy which is for the 4th electron transfer, that means if we can consider is the corresponding one for the I4 after I3, the 3rd electron transfer, it is the 4th electron transfer. So, for the 4th electron transfer, if we see that this value is low, so you can have this, because the extra stabilization of the xenon electronic configuration, cerium can be stabilized as cerium 4 plus, and that is why you can, for this particular species, you can have the corresponding oxide as ceric oxide CeO2. So, in other cases also the europium, we have seen that europium can gain an electron to form europium 2 plus. So, that gives us the stabilization for the plus 2 oxidation state having a D5 electronic configuration. And these two, that means one is in the bivalent state, another is the tetravalent state. Most of the lanthanoids have stable oxidation states in the plus 3 in aqueous solution. So, if we try to get that in aqueous solution, so it is the cerium 4 plus and europium 2 plus which can be stabilized in these two oxidation state. And now you see the corresponding E0 value, the redox potential. So, the redox potential is so important to consider over here, that the E0 value for the ceric cerous couple is 1.74, and that basically give us some idea that how strong they are compared to that of our KMnO4, that means the potassium permanganate, which is 1.51 volt. So, this particular oxidation is very close and close to that of our water oxidation potential of 1.8. So, we can immediately say that it can have some ability that it can oxidize water. So, if we can generate or if we can get something, that means the catalyst, if we want to develop some catalyst or the water oxidation catalyst, because water oxidation is a very important area of study or the research. We all know that this particular cerium, so cerium based compound involving the ceric and the cerous ion for this E0 value which will be able to oxidize the water molecule. So, which is there, and the formation of cerium 4 is therefore is favored by its noble gas configuration, that means it has only the xenon configuration. So, 4 plus we are going, so is basically the xenon configuration, the most stable one. So, cerium we get that thing, but this particular reduction, as we know, for their corresponding elemental state, the other way around, we go for plus 3 to plus 4, but if we go in the reverse direction, that means if we transfer 3 electrons to the lanthanoids in the trivalent state, and mostly it is in aqueous state, we get the lanthanoids in the solid state, how good they are for their corresponding reductions. So, basically this will give you a negative potential in the range of minus 2.2 to 2.4. So, it is all of them are very similar redox activity. So, redox activity is not very much different, unlike your chromium or unlike your manganese what we see in the 3D series. Only little bit different is europium having some potential of minus 2.0 volt. So, these potential range, so these are very simple idea for that, and we can have some good idea that why we are moving from the D elements to the F elements, the F block elements. The F block elements are very interesting to study, and they have some good applications also, because the spectroscopically what we have seen, the spectra for the 3D elements in solution, in aqueous solution, but in these cases the spectroscopic properties, when we are having some F electrons, they are having F electrons, so the F block elements, and if they are having something, that means not absorption, if they can go for some emission pattern. So, emission, if we can get like that of our atomic spectra, atomic emission for the sodium flame test. So, emission pattern, if it is different, that can be useful for some practical purposes. So, that is why we know that the general knowledge type of thing is that the neodymium. So, neodymium are very much useful or used much for the lasers, and samarium, because of their presence of more number of d electrons, because you see that we can have 7 orbitals to accommodate the electrons, and we can have, if all the 7 orbitals are singly occupied, we can get a electronic configuration where 7 unpaired electrons are there. So, more number of unpaired electrons. So, more number of unpaired electrons we can put, that means the ground state magnetic moment, we are not considered so far the magnetic properties, but the magnetic properties of the 3D elements, we know how we calculate the magnetic properties by knowing the n value. So, the more number of unpaired electrons, the n value is very high. So, the corresponding magnetic moment, the Bohr magneton, will also be very high, and this magnetic property, so it can be useful. So, these magnetic properties out of this samarium can be useful for different magnetic application. So, magnetic application, making of some permanent magnets and all this. Okay. So, is this, that means starting from is aqueous chemistry to that of thing, and this is also taken from your book, that how quickly we can remember all the reactivity pattern in a single slide, that how good they are in terms of their reactivity pattern. So, chemical reactions of the lanthanoids will tell us that it can also, because already we have seen that they can form very good or very nicely the fluorides, they can give rise to the hydroxides. So, this elemental form basically can react with water, can react with carbon at high temperature, can be heated with nitrogen, can be heated with sulfur and burns in oxygen. So, all these species, along with the elimination of hydrogen like that of our 3D metals, it can also give you oxide, sulfide, nitride, carbide, hydroxide and the halides. So, at one end we can have the ionic compounds, and other end we can have the solid compounds. So, the application is pretty wide. If we can have some useful application of the corresponding carbide compounds, nitride compounds or the sulfide compounds, we should all know how we can make these compounds very easily using the corresponding elements, because they have some availability on the earth crust, and we get this compound and we have the corresponding elemental form, and those elemental form can be converted to their corresponding compounds, and some of them are very useful as solid compound or the solid state properties are useful, and in some other cases the ionic compounds are useful, that means the ionic states are also important for those. Then we move to the actinoids. So, the other one, so is a very simple direct correlation of the actinium and its corresponding actinoid. So, the position of the actinium in the periodic table is important, and following actinium we get the corresponding actinoids. So, actinoids we get, and the positioning of all these due to the presence of the corresponding electrons in the level, which is 5f. So, the 5f level is important, like that of our 4f, which we get for the corresponding lanthanoids. So, when we talk about the 5f electrons or the levels or the electrons occupying the 5f level, we should also consider the presence of the electrons in the 7s and the presence of the electron in the 6d. So, not only knowing the names basically from the series basically, because they are also very important elements and they are having some important applications also. And this particular series, the 4f series, what we see, they are mostly important in terms of energy nowadays, because they are radioactive, and it gives, why it is radioactive, because it can give rise to the corresponding elimination of some radiations, the rays it can give. So, rays it can give rise. So, in terms of studying this actinium or the actinoids, what we can study also side by side the nuclear chemistry. So, the field which is nuclear plus, sometimes we call the nuclear and analytical. So, nuclear and analytical chemistry is enriched by studying the corresponding properties of all these elements, because they are giving rise to radiation. So, alpha, beta, gamma rays they can produce. So, these are also useful for the medical practice, that the rays are useful, the gamma rays can be useful for some treatment, the treatment of the cancer patients. So, these sometimes these rays are useful. So, these rays are also useful for the corresponding transformations, and since these are radioactive. So, most this whole series are radioactive, only some of them, that means some of them, that means like that of a thorium and uranium. So, thorium and uranium, where they are. So, we should have some idea about the positioning of these two elements in the corresponding periodic table, and this thorium and uranium are only long lived, and they occur therefore in minerals. If they are not long lived, it is very difficult to get as the natural source. So, geochemists will not help us in getting thorium and uranium from the minerals. As thorium, I told you just now that it is there in the monazite sand. So, in the monazite sand the thorium is there, and if they are very long lived. Otherwise, what we find that they are not there. So, other elements basically they will be radioactive in nature, and when they are there, that means if they are long lived, that means they are available in nature in the materials, but they have some half lives. So, these half lives are also important. So, depending upon the nature of their half lives, we just basically decay. So, some of these uranium we all know that as the nuclear fuel, because they are very good nuclear fuel. Uranium and plutonium are nuclear fuel. So, these uranium and plutonium will have some T-half values, and the corresponding isotopes we know that for uranium it is the 235 uranium or 238 uranium. So, 235 uranium and 230 uranium will have some particular T-half values. So, this particular T-half values will also tell us that after some time they will go down. That means, the radioactivity is a chapter where we see that for the nuclear chemistry chapter we also know that we can have some thing where it can go to its corresponding decay products. So, within the minerals we can also have some decay products within this particular mineral. So, this T half what we see for that uranium 235 and uranium 238, which is pretty high, which is pretty big. That means, for uranium 235 it is 7.04 into 10 to the power 8 years, and for uranium 238 it is 4.47 into 10 to the power 9 years, which is stable enough, and these two are very much useful, and a corresponding species is also useful for our nuclear fuel. So, along with plutonium, uranium can be useful for our nuclear fuels purpose. So, the positioning in the periodic table, their electronic configuration will tell us something related to their useful application, which is not in the purview of the corresponding chemistry, that means the solution chemistry or the solid state chemistry, but in terms of their corresponding application as their reactivity in terms of the radioactivity. So, their activity is different, which is a radioactive element, and they give rise to the corresponding energies for their nuclear energy or the electricity what we can make from those fuels. So, earlier members have relatively long half life. So, that is now we are discussing about this uranium and all others. So, we have the actinium, we have thorium, then we have actinium, thorium and uranium. So, along with that this other 4F elements, this can also be having that electronic configuration and have the similar type of stabilization pattern. That means, the half field level is stable and all this. So, this basically give rise to the some idea that we can have metal in the trivalent state. So, metal in the trivalent state for the curium it is 5F7. So, it will have some extra stability. So, this 0 is the actinium. So, like that of our lanthanum, actinium also will have a extra stabilization. So, that extra stabilization also we get there, but along with that thing, that means, if we just consider the corresponding change in the corresponding radii, whether we can have like lanthanide contraction, whether we have some similar or the parallel actinide contraction also. But in case of actinides, we see that the change is coming from say 111 or 103 to 98 for the trivalent state, and for the tetravalent state it is 99 picometer to 86 picometer, which is not much. So, the trend is there, that means it is going down, but the trend is not much compared to that of our lanthanide. So, electronic configuration again we can similarly involving the S, F and D subcells, and they have having the variable occupancy, because all three will have very close energy values, they are very close by. So, either you can kick out the electron from S level or the D level, or finally from the 5F level. So, it is look like 4F orbitals in their angular part of the wave function. If we consider the corresponding angular part, because both of them are of F orbitals, they are not so much hidden as 4F orbitals, and his 4F electrons can take part in bonding to a far greater extent. So, this is the only difference between the 4F orbitals and the 5F orbitals. So, these compounds basically can take part in bonding to a far greater extent. That is why if we get them the uranium, so uranium can give rise to some compound, and mostly we all know that the uranium is the corresponding uranium in the hexavalent state. So, it is uranium 6, which is a corresponding uranyl ion. So, uranyl ion is there. So, uranyl ion can give rise to some compound in the solid state. We can isolate as the cesium salt, which is UO2Cl4, where uranium, which is a dioxo compound. So, this particular species is there, which is forming as the corresponding compound as the dioxo compound. So, they can take part in bonding. So, if we just consider that you can have some sufficient thing, that means you can have the chlorides over here, this chloride over here, this chloride over here. Similarly, these two can be replaced by some other ligands. So, that we will find when we study the coordination compounds. So, if we have some O type of ligand like acetyl acetone, so these two can be attached to these and giving rise to some acetyl acetone compounds. And since the chlorides are all four them giving the charge, so that is why we know the cationic charge, but here if this is one negative charge acetyl acetone, this is one negative charge of acetyl acetone. So, this is basically a compound which is having a neutral compound. So, zero oxidation, the zero charge on this particular compound. So, this particular one compared to that other species what we have seen for the lanthanides, what about their oxidation states? So, there is a greater range of oxidation states which take part in for the involving the 5F, 6D and 7S levels of comparable energy. So, altogether we can remove electron from 5F level, we can remove electron from 6D level, or we can remove also electrons from the 7S level, and towards the left hand side, that means as we start from the group, we can get a more and more different oxidation state, that means the variable oxidation states are possible to get on the left. So, if we go for that uranium, then neptunium, then plutonium and all these cases, and americium, we see that they are having some variable oxidation states, and the stability of these oxidation states from thorium to berkelium. These are all 4. So, these are in bold letters. So, this +4 and +6, these two are mostly stable, but as you move towards the right, their stability is very less, and as we move towards Lr, the lawrencium or the nobelium. So, what we are comparing? We are comparing them with respect to the T-half values. So, uranium we have seen, then another isotope of uranium also we have seen their T-half values in terms of the decay product or the nuclear disintegration. Then if we can move down to that of our nobelium and lawrencium. So, 259 nobelium if we know, if we consider, and 256 lawrencium if we consider having atomic number of 102 and atomic number of 103, and their T-half values are very less, it is only 1 hour, and another case it is 28 seconds. So, that immediately tells us that these species, even if we can make in the nanogram level or a picogram level, so they are all synthetically made, they are not naturally available. So, these compounds, so most of them, that means all elements beyond this uranium. So, all transuranium elements, what we consider that if we are asked to comment on the stabilization or the stability of these, then all transuranium elements, they do not occur naturally on the earth, that means beyond uranium we will not get this. So, they are artificially made. So, they are very useful for their property studies and whether there is some application. So, that is why we get all, and beyond that also that considered under the super heavy elements. So, this basically gives that you already you have seen that uranium is there. So, one more thing, that means like pitch monazite, we have pitch blende. This is another natural source which is uranium compound, so uranium oxide. So, that also tells us that in the nature like that of our MnO2, we have seen earlier that as pyrolusite, MnO2 was our pyrolusite which is in the +4 oxidation state. So, what about these? So, these definitely are stabilizing. So, we have to balance 8 into 2, that means 16 negative charges. So, 16 negative charges, how we can balance? We can balance it by presence of uranium hexavalent and uranium tetravalent. So, 2 of them is as the uranium hexavalent and 1 of them as the tetravalent. So, always we get that as the in the pitch blende. So, pitch blende is our source for that nuclear fuel isolation. So, they are non-stoichiometric. So, stoichiometrically, that means the oxidation state, that means the mixed valent oxidation state like that of our Fe3O4. We all know that the magnetite what we get, that means we have both iron 2 and iron 3. Similarly, for uranium also, that U3O8 will have both hexavalent and the tetravalent, and hexavalent condition what we have seen that it has much more stability compared to the other species. So, this +6 oxidation state, so we can also correlate this immediately with that. That means what we have studied earlier, that the chromium, we have studied molybdenum, we have studied tungsten, and in some cases also the molybdenum can diaxoform, tungsten can diaxoform. Similarly, we can include this also in terms of their chemical reactivity, that uranium is also forming, because molybdenum is also forming similar type of metal complexes. that we will see when we study the different coordination compounds. Okay. So, knowing these elements from the periodic table, their isolation, their identification will give us something which we get these as the regular salts. So, whether we get these as the regular salts for their further reactivity, particularly in terms of some metal complexes like that of our UF6. So, this we can consider also as a metal salt, hexavalent uranium compound, uranium hexafluoride, or you can consider as a corresponding coordination compound that will start from our next class, that the coordination compounds of uranium, because the fluoride can be considered as a good ligand as fluoride ion. Okay, thank you very much.